So some of the reasons we like to make these carboxylic acid derivatives is that they're really important in the materials industry. Polymers you may have seen before or heard about. So polyethylene terephthalate is known as PET. It's used widely, and most likely you've heard of the nylons. This is nylon 6,6. This has to do with the number of carbon atoms that exist either in the carbon backbone or this amine portion. So in order to make polymers, what this essentially means is that these are very long molecules. So if we can imagine having this represented by a red dot, this represented by a blue dot, a polymer chain will end up having alternating red and blue dots all the way down seemingly forever, over and over and over again. So the way that this works is that we have a molecule that can't really do an intramolecular reaction very easily. So this carboxylic acid can't react with this carboxylic acid. But we do have a carboxylic acid that can react with an alcohol. So the basic reaction here is with acid catalysis. We know that we can do Fischer esterifications. We need to have a way to eventually drive off the water. So usually heat is used to be above the boiling temperature of water to drive that away. And so we know that when we have just any sort of carboxylic acid and an alcohol, say R prime, with acid, these can be in equilibrium. And these can make esters. So this is what we're going to see. We're going to have a reaction take place between this alcohol and this group. But then we could also have a reaction between one of these ethylene glycol molecules and the other side. Over time, each half of the molecule is able to react over and over again. So on one side of the molecule, we can have one of these carboxylic acid groups react with an ester. Then this acid will react with another molecule of the monomer. And over time, we build up these very, very long strings of molecules. We end up getting a repeating pattern as shown. Note that there is this N here. N is equal to number of repeat units. So depending on the type of polymer, this might be 50. This could be in the thousands. Some polymers are very, very long. And whenever you end up reacting single molecules and making them into a giant macromolecule, they end up having a lot of immersion properties. And so anytime that you have this sort of system where you have two functional groups on a molecule and two functional groups on a different molecule, these can react to make polymers. Sometimes you have actually one where you would have functional group A here and A here. It's able to react to the functional group B and a functional group B. You could also have A and B on the same molecule so long as they can't do an intramolecular reaction. Similarly with the amides, simply mixing together the carboxylic acid and amine, these make initially the ammonium salts that we saw before. So regardless of whatever structures these are. And then again, with a lot of heat, we're able to make an amide bond by driving off water. And this is a similar situation where each of these amines and acids will be able to find one another. They end up reacting. Cyclizations are largely minimized by running these at very high concentrations. So usually in the salt form already, they make a interconnected salt that already makes a sort of charged ionic polymer, and then heating it up makes the covalent bonds. So one of the hardest parts in predicting a polymerization isn't necessarily the basic reaction, it's defining where the brackets go. So here we're asking, can we draw the structure of a polyurethane from the two reactants shown, this bis isocyanate and ethylene glycol? So we already know that the basic reaction of an isocyanate and an alcohol will be an addition to give us a urethane linkage. So the challenge becomes, how do we draw the right structure? How do we get the brackets in the right place? So one way that's fairly useful, there's a lot of different ways you can draw this, and technically, as long as you have it in the right relative orientation, you can put the brackets wherever you want. So I'll draw out the benzene rings. And let's imagine the addition product from each one of these with a single molecule. So the goal is for the repeating unit to be represented, and that repeating unit will have exactly one molecule of each of the two monomers. So right now, the molecule that's drawn has too many atoms because we have two ethylene glycol molecules. So all we need to do is essentially choose the brackets where we want to put them so that we end up with a repeating structure that is correct. So we could choose to put a bracket on this side of the oxygen. If we do this, then we need to put it on the other side of the corresponding oxygen. So we can see that on one side we have two carbons and an OH from ethylene glycol, and we have another OH from the ethylene glycol on the other side. Within, we have oxygen, two carbons from ethylene glycol, and then all of the functionality from the isocyanate contained within as well. I'm going to erase these just to make it a little prettier and consistent with the other side. It's an NH. And we'll put an N down here for the number of repeating units, just to kind of highlight how we can go and change the structure. We could actually move these brackets around. Let me show you another place you could have put the brackets. We could have chosen to put it directly in between the two carbons. Could have shifted it over once. This still has the same proper number of carbons on the inside and outside of the brackets. Let's do one more, something maybe a bit more exaggerated. Where else could we have put the brackets? If we were to go and even draw this hydrogen out explicitly, we can put it all the way over here. Now we just want to make sure to be on the inside of the next oxygen. So this would be drawn right there. So all our correct brackets need one molecule of each monomer within. So it's a bit of your choice where you want to make the breaks, but I think in a case like this, most of these types of reagents we'll look at have two additions. So I would draw the double addition product and then draw the bracket so that you only have one. All right, I think that is all the slides to end this subsection. Next time we'll head into amines. Next week we'll be talking again more about the class format. You can give me some feedback on how this type of presentation worked, if there's anything I can do to help clarify. And of course, feel free to provide feedback through Piazza, by email, or whatever means works for you.